Problems. Oh boy, Mr. D, I'm so happy you're going to do this. I love word problems. I wish mathematics had more word problems. I know. It's a shame we don't do more real life problems. Anyway, for quadratic application problems, we have pretty much a special equation here, um, using a lot of height and the maximums of objects being thrown up or landing and hitting the ground. And maybe there's certain times we want that to figure out what height it hits. So we use this equation h equals negative 16t squared plus v sub o or v0 times t and plus h of 0 or h0, however you want to say it, where h is the current height. So we're solving for the current height in a lot of these problems. Think of that as your y, right? Y equals ax squared plus bx plus c is our standard form of quadratic equation. So our h is the current height, represents the current height. The t, well, seems pretty obvious that t would be the time, and the time is in seconds unless otherwise stated. V sub o or v0 is our initial velocity. And h of 0 or h0 is our initial height. Now, this negative 16 is a constant factor. You guys familiar with E equals mc squared, right? Where c is always a constant in relative. Who's in physics in this class? Any physics? You probably can relate to a lot of this, right? Do you know what that negative 16 is? It's a constant. It's what we call acceleration due to gravity. Gravity. It's a gravity constant. So that negative 16 is gravity. Okay. And the speed of that is, it's measured in feet per second. Feet per second, actually, second squared? Yeah, second squared. I'm not a big physics fan and never was. And I wish I did, because math and physics really tie into each other. So that's what that negative 16 coefficient is. Now, we're the only country, I believe, that uses feet per second, right? Most other countries use metric system, right? So it's different if a lot of problems or real life problems are actually given in the metric system because the rest of the world does. Well, it's not negative 16 because that's 16 feet per second squared, right? It's actually measured in meters per second, and the constant coefficient is negative 4.9 meters per second squared. So, depending on what you're talking about or where you're talking about. Uh, if you see 16, you know you're doing an American problem. And if you see negative 4.9, that means if you're talking every place else but the US. All right. You guys ready to do a little quadratic modeling? All right. A rocket is launched directly upward at 45 feet, feet per second from a platform 70 feet high and is given by the equation the S of t equals negative 16t plus 45t plus 70. What is the S of t? Well, that's just function notation again, where once we find t, we can plug it in there and yes, ma'am. Yes. That's the given seconds, okay? Just like VF of x. If you're given a value for x, you plug it in wherever there's, it's function notation. What is the initial velocity? Well, let's figure this out. Okay, now here's all our definitions of our variables, right? So it's asking us what is the initial velocity of the object when it is initially launched? Well, our initial velocity was v sub volt. So if we look at our general format equation, here's our initial velocity, right? So what's the coefficient there? 45 feet per second, right? That's our initial velocity. I should put feet per second. What will be the object's maximum height? Well, that's something we have to figure out. How many seconds have elapsed when the height will be reached? Again, that's what we're going to have to figure out and show the heights for the following times. All right. So you're going to need your graphing calculators. There's no way around this. That's why I'm hoping that we do most of the practice work here in class. So you're going to probably need to pay attention. Otherwise, you're going to need your graphing calculator for this. All right, so in your y equals, now we're not going to be able to use these variables, the s, the t, but we're going to use x squared instead because that's what our calculators have for a variable. All right, so I'm going to go ahead and put this equation in there. I've got negative 16x squared, so negative 16x squared, and you're going to want to punch this in and do it with me because all of the problems you're going to have to do like this, and you're going to have to we're going to be fidgeting with the window so we can see it. So you're going to need to practice on using the calculator. Okay, so go ahead and get a calculator. Make sure you get a calculator, and work with me. Okay. All right. So I have negative 16x squared plus 45x. So plus 45x and plus 70. So I'm going to draw a little picture too what's happening here. So we have a rocket. I'll put it over here. And we have a rocket here that's launched upward and has initial velocity, and eventually it's going to run out of speed, right? Either it's going to run out of fuel or um, it's going to have to come back down to Earth. if it's a big rocket. It could be just a rocket on a model rocket, and then it's going to hit the ground, right? So again, our initial velocity is 45 feet per second. So that means that this axis is, we don't call it the y-axis. It's our height. It's our height. So this is our height, or our h axis, right? Well, if that's our height, we start here. We're going to go up. Our x axis is no longer x, it's time, t, right? Okay, so here's kind of like the picture of what's happening. My rocket's launched, it reaches its maximum height, and then it hits the ground. So there's my equation for the rocket. So let's see where it lands. Oh man, I don't even know. So this is what I mean about, we're going to have to work with the calculator here to see where this thing is, so I can get the whole picture on my window. So to adjust this window, looks like this parabola is going way up there, right? I'm going to go to my window here. Notice that the x minimum is negative 10. So if I look at my graph, there's my origin. My x minimum here is negative 10. So it goes out to negative 10. All right. And it goes out to positive 10. So there's positive 10. It looks like my x axis is okay, because I could go to like negative 5 if I wanted to zoom in a little bit. So if I want my x minimum negative 5, see how it's shifted over here now it's negative 5. So it kind of zoomed in a little bit. I kind of like that. Now my x, I have no idea how high this is. So this would be my y maximum, right? So I'm going to go back to my window here, try to get my vertex on my screen. It's going to be my y maximum. And I'm going to put, oh, I don't know, I'm going to put 200 in there just to see if I can get that parabola in there. And sure enough, I get my parabola. I get my vertex in there because that's what I'm looking for, right? I'm looking for this vertex because they want to know what's the maximum height. So I need that vertex to determine what that maximum height is, right? Okay. And I'm also going to need how many seconds it gets there. So remember, this is my time. So I need my seconds here and my height here, which is in feet. Okay. All right. So let's look at the object's maximum height. Remember, that's an h comma t is what I need, right? Maximum, or I'm sorry, we always do the x-axis first. So that's going to be t comma h. So I need to find both of these, my vertex. Now, I'm going to go to my calculations on my calculator. So I'm going to hit the second button. I'm going to hit trace. And I'm looking for the vertex, which is a maximum, right? So I'm going to go down here, highlight maximum, and I'm going to hit enter. Now, notice on my calculator, it's asking me for the left bound of that vertex. Well, see where my cursor is, right? I need to get it to the left bounds, to the left of that vertex. So I'm going to use my arrow key. That's why you should be on a calculator practicing this, because you're going to be doing this by yourself. And on the quiz Friday for math modeling, you're not going to be able to come to me and say, how do I do this? You should be doing it with me on your calculator, not your phones. Let's see, 1, 2, 3, 4, 5, Six phones out? I don't know how you're going to do this on the quiz Friday. All right, so I got to get to the left of the vertex. Okay, I'm clearly to the left of the vertex here. I'm going to hit enter. There's my left bound. Now it's asking me for my right bound, so I'm going to get to the right of the vertex. So I'm going to go ahead here and get to the right of that vertex. Hit enter. There's my left and right bound, so it's going to take that space there and determine where that vertex is. So it's asking me, do you want me to guess where it is? Well, yes, I do. So I'm going to hit enter, and it's giving me that point. Okay, it's giving me that t comma h. So my t comma h is 1 point, we'll say 1.41 comma 101.64. 101.64. So there's my vertex. Okay, there's my vertex. 1.41 comma 101.64. Now remember, this is my t or my time, so this is going to be 1.4 seconds and 101.6 feet. Okay, so what will be the object's maximum height? That's going to be 101.64 feet. How many seconds have elapsed when this height will be reached? Well, 1.41 seconds. Okay. Now it wants us to give us the heights at the following times. So again, this is 1 second, this is 2 seconds, this is 3 seconds. So to get these values, I'm going to go back to my calculator. I'm going to get my table. I'm going to hit second graph. And again, these are on the x axis, right? This is the x axis, is where I have my time, and my height is on the y axis. Okay, so I'm going to look at the x axis at 1 second. When my x is 1, there's my x. My y is going to be at 99 feet. When my x, or when my time is at 2 seconds, my height is going to be 96 feet. And when my time reaches 3 seconds, my height is going to be 61 feet. So it's going to my maximum height's 101. If it's at 99 and goes to 96, I'm on the downside of the slope, right? I'm on the downside. The rocket's going towards the ground at this at 2 3 seconds. All right. Find the average rate of change. Now, what is the rate of change? Slope, right? Slope. So my slope, if I was just dealing with regular algebra, slope is rise over run. In mathematics, it's the change of y over the change of x. But because we're dealing with applications and we're using um, height and time, it's going to be the change of y. My y axis is my height, so it's going to be the change in height over the change in time. Okay, so my slope is actually the change of height over the change in time. But just like we would take our x of 2 minus x of 1, or I'm sorry, our y sub 2 minus y sub 1, and our x of 2 minus x of 1, remember? I'm going to take two of these points. I'm going to take, oh, I don't know. I'll take, I might just get a really, I don't want to take it because that 99 was on the upside. Okay. And because it was at 1 second, we didn't reach our maximum until 1.4. So I'm going to use 2 and 3 seconds. Okay. Because these were on the same side of our, it was coming down. This was before the vertex. These two are after the vertex because they're after the 1.4 seconds. So I'm going to take three, my height, which was 61 minus 96, divided by 3 minus 2. So 61 minus 96, let's see, 35 over 1, or, and we can't measure time. So it's going to be the height feet, 35 feet per second. And we're not going to use the negative because, again, distance has to be positive. I'm going to use the absolute value of that 35. Easy peasy, right? Thank God you guys focused and used the calculator to go along with me. All right, let's do another one. So, what happens if we just drop the object as opposed to launching it? What part of the function from above changes? Okay. So, if we just drop it from a certain height, we're at 120. What do we lose here in this part of the graph? If we're just standing up here at 120 feet, yeah, Ben. Yeah, very good. Because this initial velocity gets us up to that point. Okay, so we actually lose that initial velocity. Okay, again, if I draw my little graph here, picture of what's happening, because it always helps. This is my h axis. This is my t axis. Okay. Um, let's see. We're going to start at 120 feet, right? Okay. If I just drop it, we lose that initial velocity. We don't need velocity to get up to that point. Okay. So if I look at the equation here, so this 120, that's my initial height, right? So if I go back up here and look at my definitions, my initial height is h of 0. So that's my h of 0. I don't need the initial velocity, the v sub 0. So I'm just going to take that out of the equation, right? So I have h, and that's my cursive h, by the way, okay, equals, I got to have that gravity, no matter what, I always have to have the gravity constant, negative 16, t sub squared I'm leaving out the velocity, that whole velocity, like say I have negative 16 t squared plus velocity t plus h. I'm leaving that whole term out because we don't need it. So plus initial height h of 0. Yeah. Well, I know that the h of 0 is 120. So h equals negative 16t squared plus h of 120. My fault, because that's my initial height. So they're asking how long does it hit the ground until it hits the ground. So it's looking for this amount of time. By the way, what do we call this point where it hits the t axis or the x axis? Remember, we did it in regular algebra. It'd be the x. It's the x intercept, right? It's the x intercept. In this case, it's the t intercept. What's the value of h at this point? 0. Yeah. So we're looking for when h equals 0. Okay. So that's where that whole s of t function notation comes from. All right. So we got to find out what t is. We got to find out this amount of time. So again, I'm going to go back to my calculator here. And for the y equals, I'm going to put in negative 16t squared, negative 16x squared, and plus 120. So plus 120. And I don't need that. Got a delete button, delete, delete. Okay. Now remember my window parameters I messed around with last problem, right? I'm just gonna graph this and see where it's at right now. Well, it's not too bad actually. Um, Notice that I really only need this quadrant, quadrant one, right? I only need this quadrant. If you want to play around with your calculator, you can get your calculator to just show these this quadrant. Like I could put for my t maximum or minimum, I could put like -1, right? I'm going to go back to my window here. I can actually put -1 there just to show a little bit of quadrant 2. I don't need quadrant 3 at all. So my let's see, be my y minimum. I'm just going to put as 0, okay? Because I don't need 3 or 4. Okay. My max wasn't that bad. I might lower it back down to 150. Let's see what happens here. Yeah, it's not too bad. Okay. So I want to find. Maybe I'll go a little bit more. Um, let's see. My y minimum. I might go to -1, just to see if. Yep, I want my where it crosses. Okay, so it looks like it hits the ground between. Oh, let's see. I got 2 seconds. 1, 2, and 3. So between 2 and 3 seconds, right? That's when it's going to hit the ground between 2 and 3 seconds from my calculator. I have to know. I might even open up that window a little bit to -5 here or -10. Okay. Now you can see it better. Between 2 and 3 seconds, right? So I need to know when my y is equal 0. Now I could maybe get lucky and they have a y zero y in here with a zero value. Nope. So I'm going to have to use some calculations. So I'm going to go back here and do some calculations. So I'm going to hit second trace, which is my calculations. This time I'm looking for the zero, right? The h equals zero. So I'm going to highlight zero and do my left bound. Let's see, I got to get back to 2. There it is. Hit enter. Then my right bound, hit enter, and hit enter again. And my zero is at 2.74 seconds. So it hits the ground at 2.474 seconds. So that's the first part. I'm not going to do any homework. I'm going to continue working on the no packet here tomorrow. Okay. So I'm not going to give you the homework sheet for this.